Okay. Why isn't this projecting? What's going on here? Come on.
Time.
Do. Come on. I'm connected.
What is...
There we go. Yes, Wookie, what's wrong?
What is the benchmark point of your CPU in this lesson?
I don't know, what is it? It's probably like, I don't know, maybe 1.2. I don't know actually. I know it's a gigabyte of RAM. I know that. Actually, maybe. No, okay, where are we now? Fields, induction. Okay. Hard. Not so bad. What was our last slide? Where did we stop?
Graph.
The graph? Oh yeah, the graph. The generator. Yeah. Yep. Okay. Okay, we saw the generator. Yep, nice. Right, okay. So we got this last time. And I've seen them ask students to draw this in the exam a couple of times, and also to draw the position of the armature underneath as well. So I've seen this in the exam. So just make sure you still you have this in your notes, because we were kind of rushing this the last day. Make sure you have that still. Did everybody manage to get this last time? Yeah. Okay. So we'll continue. It's worth saying actually that here these are AC. This is coming from an AC generator. So in fact, if you were to measure the voltage here, you'll see the voltage will go positive, negative, positive, negative. It switches back and forth here. Because this is how the electricity is made using the AC generator. I wonder, does anybody know actually how quickly it changes direction per second? I think it's the same in most countries. How quickly does the positive and negative change back and forth? Does anybody know the frequency? No? Nobody knows this? No? It's about 50 hertz, 50 times a second. So in 1 second, it has switched direction 50 times. Yeah, there's 50 cycles in a second. And I think this is pretty standard in most countries. Yeah. So what this tells me is per second, this wheel that's turning in the power plant, it must turn 50 times a second. Must do. Okay, so continuing. So we haven't actually given the definition of AC. We've talked about it. We've defined it. So alternating current is an electric current in which the flow of electric charge periodically reverses direction. What does this word here mean? Periodically. You can't give a definition like this, okay? What is potato? It's the potato. Periodically is what? Yeah, circular. Repeated. Okay? So it repeats in changing its direction. Just compare that. Now, you don't need to write the second half down, I suppose. You just need the first half. But just to compare that with DC, well, did you write down the definition of DC? Did you not? No? Oh, well then you better, I'm sorry, well, you better write this down if you didn't. Whereas in direct current, DC, the flow of electric charge is in only one direction. Okay, yeah, sorry, you need all of this, I guess.
there any advantage to change the direction?
Yes, there are advantages and disadvantages. So, the big advantage of AC instead of DC, well,
Okay.
I'll show you once people write this down. Okay, you got that? Yeah. Who's still writing? You're still writing. Anybody else? So, Wookie was asking me, is there any advantages or disadvantages between AC and DC? And that's a good question because, for example, here is AC, but the battery, like inside the laptop or inside your phone, that's DC. So is there any advantage or disadvantage? And there is actually. So I'll give you, if I can draw it for you. Oops. Right. Where's it gone? Okay, here we go. So you have your power plant. Come on, there we go. Try and draw my power plant. So there's the smoke. It makes electricity. That's a power plant. And you know, the wire runs across a very, very great distance and then enters the town. That's a house. Now, you understand, of course, that there's a resistance in the wire. This is like a large resistor. You have a formula for how much resistance there is. It's R equals rho L over A. Now, this is because of the material. So I'm not sure, but I have a feeling that this power line, you know, the big pylons, I think they use steel. I don't think they use copper because that would be too expensive. I think they use steel. So anyways, this would be quite low. This here would be actually quite big. Because if you've ever seen these cables, they're fairly big cables, you know. But unfortunately, this here, this would be quite large. And you can't really change that. You know, this could be something like, I don't know, 50 kilometers. So it means that there actually is some resistance in the wire, and this resistance takes the form of heat, which means some of the energy is actually wasted. Does anybody know how efficient the efficiency getting the energy from here to here is?
Less than 40.
Less than 40?
Yeah.
Not that bad. I was watching a documentary about it. They said it was 50%.
Oh, that's good.
Do you think 50%? It means for every 2 joules that's made here, 1 joule makes it to your house. I don't think that's that good.
Okay.
Anyways, this formula here, that is actually the formula for DC. The resistance, if it's DC, is this is if it's DC. If it's AC, it's actually, it's roughly something like this. Now, before I continue, I should say this formula is not part of the syllabus. I just want to show it to you. It's something roughly like this. Roughly. So, which produces more resistance, AC or DC? AC. Which seems a little bit strange because that's what they use. So why do they use AC? Well, you have learned last time that the electricity is made in the form of AC. And in fact, if you wanted to change it into DC, you would have to spend some energy to do this. This conversion would actually be more than how much is wasted. So they don't bother to change it. They just send it, and they are willing to accept, 40% extra resistance, because the cost to change it from AC to DC is very great. It's very difficult to change AC to DC. So they just let 40% extra resistance by using AC. So it's more efficient to use DC. If you can use DC, you should. It's you can see it's a big difference between the two. More efficient to use DC. Yeah. So anyways, the difference is important. Okay. Do you have this?
Yes.
Not yet? Okay. In the future, it might be possible that more homes use DC. Your USB connection, like this thing here. You probably have a lot of things in your house that use this. Tablets, smartphone, headphones. These are much better than this, because these are DC. They're more efficient. And you probably have seen in some homes that you now have 3-pin and USB up the top. You're starting to see those, okay? So perhaps in the future we will have only USB. Perhaps. Okay, have you got that, Bruce? Oh, come on. Which word are you on? Last 3 words? Okay.
Why Apple choose that USB-C type?
Why's that?
Why Apple, the company, choose the USB-C type? Is there any difference?
Yeah, there's different. The newer USB connections can carry more current. So I think that the first USB maximum is, 1 amp. I think the new USBs can go to 3 amps. I'm not sure, but that's the reason for the different USB connections. It's their maximum current. Yep. Okay, continue. So, you know from the graph that the voltage changes from, well, I guess that's fine. V max, minus V max to V min. So when you look at the graph, it goes like this. There's a maximum and there's a maximum underneath, or a minimum. Okay. Whoops. So we'll call this one here V max, and this one here will be minus V max. So the question is, what number should we use? Like here, this voltage is 220 volts. But what is that on the graph? It's not actually the V max. It's an average. But the problem is, if we take an average, the average would be 0.
Yeah.
But when we look down here, we don't really care that it's a minus.
Yeah.
That's not important. So actually, we kind of imagine the graph is more like this. We don't really care about the minus. So what would be the average? You might think it could be something like V max over 2. But it's not actually quite like that. The reason for that is because it's not linear. Let me show you. If you had a graph like this, let's say it starts at 0 volts, and let's say we'll call this V max, and it goes up to V max, and then it goes back down. Then here the average voltage would be V max over 2. But when it's when it's not linear, when it's curved like this, the formula actually changes. I wonder if anybody knows what it is. No? I don't, so you haven't seen this one. It's V max over root 2. So when the voltage varies from V max plus to V max min, the average is actually V max divided by root 2 instead of 2. And this is because of its curve changes the formula. So when you feel that this is 220, it means its average is 220.
The number of 1 over root 2 is related to tangent 45?
Not related to tangent 45, but it is related to the fact the graph is a sine. Now, unfortunately, you don't do this in maths class.
Yeah.
But there is a way to calculate what the average of a sine graph is. Yeah. What's the voltage in South Korea? 110 or 220? 220?
Yeah.
Is everybody here 220 back home?
Not common.
Or 220 to 240 is, yeah, common. A lot of appliances that run on 220 are designed to run on 240. There's like a window that's acceptable between 220 and 240. It's only a problem if you go to, say, a place that uses 110. And nobody here is a 110 country, no?
South Korea used that 110 and changed to
Oh, you changed it?
Yeah.
How long ago?
maybe 40 years.
40 years ago.
40 years ago, I think.
Long time ago. North Korea, still 110?
We don't know that.
We don't know?
Yeah.
Okay. Well,
Maybe-
that's if they
maybe
have
110.
electricity.
Yeah, maybe 110.
Maybe 110, yeah. Okay, continue. So, finally, do we have a handy way to figure out which way the induced current will flow? The answer is yes. Yes, we do. It's called the right-hand rule. Don't confuse it with the left-hand rule. So the left-hand rule was to tell you the force. The right-hand rule is to tell you the current. So, if I try and just maybe draw here before, so let's say this is north, this is south, this way is the field, and then you have something like here, yeah, maybe we'll have something like this. So this wheel is turning this way, so there's a force acting up here, and I would like to know which way the current is. Is it coming out to me, or is it going into the page? Well, let's use the right-hand rule. So the right-hand rule says force is up. This is the field. The field is to the right, so it's in. The current induced is in. So we'll get a current that is going into here. So this is the Fleming's right-hand rule. If you can draw that, please.
Draw. Okay. This is only for induction.
Yep.
Or
Yep.
Right hand.
right is
Motor,
yeah.
generator.
Motor and generator.
Yep.
DC you mean.
And don't forget right-hand grip rule.
This is everything.
And this is for a current. It's magnetic field around a current. Right hand. You have right hand grip, Fleming's left hand, and Fleming's right hand.
Which one's generator?
This one's the generator.
This one.
Yeah. DC motor, left hand.
Yeah. Ah. That's right.
Don't mix them up in the exam.
What did you mean by left-hand rule gives us the force?
Yeah, so in the left hand rule it is for the DC motor, so you would like to know which direction is the force, because you usually want to figure out which way the wheel will turn. So you want to know which way the force is. It's also the rule, it's also, the left hand rule is what you use in the formula F equals QBB. You need the left hand rule for that, to work out the direction of the force. Yeah, there's a lot, you see, there's a lot here in this section to remember. Yeah, continue. Continue? No? When you have a direct current and you want to know the magnetic field around it, its direction. So, right hand grip rule here would tell me the magnetic field is going this way around. If the current is going to you, it's going this way around, using the right hand grip rule. Yeah.
Is there another rule?
Another hand rule?
Yeah, right.
There is not.
Left.
Not
foot.
for us to study.
Left foot.
Left foot rule?
Left foot rule.
No.
That's it. Okay.
That's it. Okay, continue. Yep. So, a final hint before we look at some examples. Note, normally, when we look at the change in the flux, the magnetic flux, it's usually either the B or the A changes. But for our problems, not both. So the good news is, when we're considering... Where's it gone? Oh, upside down. When we're considering this, which equals the change in this, it's either going to be the B is changing, so it'll be area times the change in B, or it'll be the other one. It'll be the B is constant, but the area changes. They never give you a question where both is changed. That's just too hard. Just too hard. So it's basically it's either going to be A delta B or B delta A. It's going to be one or the other. Okay. The delta B is if the B changes, and the delta A is if the area changes. Usually a swept out area, which I need to explain what that means. I'll draw that in a moment. Can you just make some note here? You don't have to write all of this down, but just make some note. I'll explain what I mean by swept out area. Yeah? Let me explain swept out area. Okay, can I draw? So, the first one is easy if the B changes. So that's usually something like you have something like this, and there's a magnet here, north south. So when you look inside here, the B is 0. And then later when you look inside, the B is not 0 because maybe now the magnet is inside of it. So we went from no B to B. Yeah? The magnetic flux density. So we have the formula flux equals BA. Yeah. In this particular example, I guess it's more like NBA because we actually have it wrapped around N times. Yeah. Anyways, this is an example of when the B changes. Another example would be like this. Maybe let's take something easy. Like maybe we have a copper wire, and here we have a magnet. We'll say north south, and then I flip the magnet around south north. So as I'm turning the magnet, I'll get a current here. A current will flow. Yeah. So like for example here, the magnetic field is north to south. Whereas, Sorry, that's stupid.
It is.
Yeah, no, it's sorry. I do the same thing. Sorry. South, north. So here the magnet goes north to south, just like that, and here it goes north to south. So in this picture here, we could say maybe the B is like minus 1 Tesla because it's going to the left, and here we could say the B is plus 1 Tesla. So what's the change in B? That would be 1 Tesla minus 1 Tesla, that would be 2 Tesla. So it's changed from being negative to positive. Now, because this is positive, what does Lenz's law say the current's direction will be? Opposed to change. So the current will be going which direction here? If I flip this magnet around, I'll cause the current to flow to the left or to the right? Which way? To the left, yeah, to the left. So now I'll have a current flowing to the left. In fact, I can work out how much the voltage is by using my formula, minus change in flux over change in the time. Yeah, I just literally, it's like this, look, here's the wire, okay, and I have a magnet that's beside the wire, and I just pick up the magnet and flip it around and put it back down.
And the current will go
in the opposite direction to the change here. So now remember, the current is only present as it's changing. As soon as I stop moving it, the current will disappear. It's only while it's changing do I get the current. Yeah?
And in this situation,
Yeah.
the current is flow or not?
Right now?
Yeah.
No.
No, and if
But
you
the
change,
moment I pick it up and start turning it,
yeah.
I get a current.
Yeah.
and it goes
Still have a current, yeah. Now no current.
While you're turning,
While I turn, I get the current, yeah.
and the current also opposes.
Yeah. Here, what I'm doing is, the magnetic field's going to the left. As I'm turning it around, I'm moving it in the direction to the right, causing the current to flow to the left, opposing the change. Yeah.
In both examples, B changed.
In both cases, B has only changed. Yeah, yeah. The area hasn't changed here. The area, I guess, is the would be like the cross-sectional area of the wire. And here, actually, what would be the area here? What's the area in this picture?
Area.
Yeah, yeah. It's a circular area here, because that's the area that's being cut by the magnetic field.
Do we
Yeah.
just measure one?
Yeah, we just measure one and we're multiplying it by n, because it's looped around, yeah. Okay, well that's B. Now, what about if the A changes? B is a vector, yeah, or at least it has a sign. No, it's a vector, yeah, vector. Yeah, because in the formula F equals Q V B, the Q is a scalar, the V is a vector, and the B is a vector, and we have this special multiplication called cross multiplication, which is regular multiplication but with a direction using the left-hand rule. Okay, next one. What does it look like if the area is changing? Okay, so that would be something like this. Let's say you have a north here and a south here, and the field is going this way. Let's make this a pretty big field. And let's say I have cutting across the field a wire, and I drop the wire. So it's going to fall down the field like this, perpendicular to the field. So if the field is going to the door, I'm dropping a wire down the field like this, perpendicular to it. Okay. In this case, the B is not changing. The B is constant. What is changing is the area. And you might say, what area exactly? Because this here, imagine this radius is 0. It's not the area. It's not the area here. Anyway, that area doesn't matter because it's only the perpendicular you care about. So you don't care about this area, only the perpendicular. So what area is changing here? Well, what's happening is as this falls down, it's making an area. It's like drawing a rectangle in space. How quickly that is drawn is the delta A. So for example, let's say it's falling at a steady speed. We know it's not falling at a steady speed, it's accelerating. But let's just say it's falling at a steady speed. So let's just make it easy. This is 1 meter. And when it falls 1 meter. And then another second later, it falls another meter. How big are these areas? They're 1 meter squared. And how quickly do I get them? I get them every second. So it's 1 meter squared per second. That's the delta A over the delta T. It's how quickly the area is being drawn. Do you understand? It's like how quickly I make the rectangles. Now, if you want, you can draw this because there's actually a useful formula you can make here. For example, voltage equals minus N delta flux over delta T. That equals minus N. What's changing here, the B or the A? A. So that's B delta A over delta T. But what is A? Well, let's call this wire length L, and we'll call this distance here, we'll just call it S. So that would be minus NB. Now, which is changing, the L or the S? Only the S. So I'll take the L out, and I'll write here delta S over delta T. But what's delta S over delta T equal to? Speed, yeah. It's how quickly it's falling. So we could write this formula as minus NBL times speed of how quickly it's falling. So we can say the voltage of this falling wire, or moving wire, is NBLV. Now this formula is in the formula book. I don't really use it. I prefer to stick with this one formula for both. But if you prefer it, you can use this one. It's what's in the formula book. Yep, this is actually the same as this if the A is changing and not the B. So if B is fixed and A changes. I think you should write this down. I know, that's why you should write it down. This lesson is very hard.
Yeah.
So the faster it falls, the more voltage it makes. Also, the longer the wire, the more voltage it makes. I suppose in this case here, if you're looking at just one wire, then you don't really need the N here, if it's just the one wire. So I suppose you could even just simplify the formula as minus, and if you don't care about the direction, it would just be BLV, boulevard. Yeah. Yeah. Now you might be wondering, what do you do if the V keeps changing? So for example, if it starts at rest and then it accelerates up to a speed of say 10 meters per second, well, as it falls, it's getting faster and faster. What's happening to the voltage? Increasing or decreasing or staying the same?
Increase.
It's increasing, isn't it? In fact, when will the voltage be greatest?
Dun, dun.
Just before it hits the ground,
Yeah.
when it's travelling fastest. Sometimes they're a little bit sneaky in the exam. You have to read the question carefully, because sometimes they ask for the voltage just before impact, which means you should use the V at the end. But sometimes they ask for the average voltage as it's falling. So what V should you use for that?
10 over.
You should use the average V, which would be what? Be something over something for sure. It would be U plus V over 2.
Not the square.
No, because that one is only for the generator. Oh no, that's a good point actually. No, but not here. Because this is linear. You have to be careful about that. The person who writes the exam at the moment tends to prefer to ask the student what is the voltage just before impact, which would require us to use V. The previous exam writer prefers to ask what was the average voltage as it falls. Then we would have to use U plus V over 2. Yeah? Continue? Okay, let me just Right, after all of that, we can now look at some examples, okay? An insulated copper wire is wrapped around a metal pipe, which is 30 centimeters long and 5 centimeters wide. So let me just draw that for you. So we have a pipe, 30 centimeters long and 5 centimeters wide. And we wrap a copper wire around it. And we wrap it around 100 times. And we take a magnet of 1.5 Tesla, and that's moved through the pipe over a time of 3 seconds. What is the average voltage induced through the copper wire at the moment the magnet is inside the pipe? So, a question's a little bit unclear. I'll draw it to be a little bit clearer. So, we have a magnet here, that's 1.5 Tesla, and then we move the magnet to be inside the pipe. And it takes us, we'll say it takes us 3 seconds to move it in. So, it's at the beginning, it's right outside the pipe, and then it's in the middle of the pipe. That took us 3 seconds, and it's a 1.5 Tesla magnet. And my question is, what is the voltage we get inside the copper wire? How much voltage do we make? Okay. So which formula do we need here?
N times.
N times change in flux over change in time. And which is changing here, the B or the A? The B is changing. It's changing from what to what? It goes from what to what? Yeah, it goes from 0 to 1.5. Yeah. I don't care about the direction, okay? I don't care about the direction. I just want to know how much voltage. Can you calculate that? So in this case, I don't care about the direction. help you out a little bit here. It's the B that changes. We got answers? So this will be 100 times pi times r squared over 1.5 minus 0 over 3. Alright, so what do we get here, please?
0.098.
0.098. 98.2 millivolts? Yeah? Did we all get that? Not much, not much. This is okay? Guys over there, is this okay? Yes?
Yeah.
It's okay? Alright, next example?
Yes.
Okay. So, next one. A plane takes off heading towards Santa Claus at the North Pole. Yep, you know Santa Claus, of course.
Yeah.
Yes, yes. The magnetic flux density for the Earth is 0.07 millitesla. The wingspan of the plane is 60 meters, so the distance from the end of the planes is 60 meters, from the left to the right tip. Total. And it's climbing at a speed of 250 meters per second. So I'll just draw that for you. Okay, so here's the picture. If I look from the sky as a bird, okay? So, sky view, yeah. Sky view. So here is the North Pole. Where Santa lives. Okay, and here is our plane. Air Force One, indeed. Air Force One. And the distance, okay, look, I'll even put on the little, there, okay. The distance from here to here is 60 meters. Okay. And the climbing speed is 250. So what I mean by that is, if I was to look at a side view, here's the ground. What does the plane look like from the side? Here it is here. Here it is here in the air. There's the wing. Okay. And here is it's heading to the left. The climbing speed is 250. What I mean is, this here is 250 meters per second. It's gaining height of 250 meters per second.
Oh, okay.
Yeah, not that it's flying at 250 or it's going forward to 250, but every second its altitude increases by 250 meters. Its height.
This is heading to the north.
As it's heading to the North Pole. Which direction is the field here? Yeah, up or down?
Down. Ah!
Where's that?
Down.
Up.
Oh. What?
Because remember,
This is Earth.
yes,
Okay.
the North Pole is the south end of the magnet. Yeah. Now, what is changing here?
A.
The A is changing.
Yeah.
So you could actually use that formula I gave you, the BLV,
Yeah.
because the N here is only one. Why? Well, it's just one wing span. So the N is 1. And I don't care about the direction, so it's just the formula BLV. So the voltage, the EMF, that is just B LV. Nice and simple. Okay, what do we get?
What's the number?
Oh, sorry, well, let's go back to the question then. So, give me the, do you need me to go back to the picture? No? Yep, looks good. Okay, got an answer? What did you get?
1.2.
Yeah. 1.05 volts. Now think about what you're saying. What you're saying is, if you connect a voltmeter around the plane, that voltmeter will read 1.05 volts. So,
That's interesting.
it is. Now, tell me this. When will that voltage read 0? No.
Before
While it's landing, it still says 1. It still says 1 volt. I think I'll just say minus 1 volt. It's descending. Well, if it's not moving, okay, but forget about it not moving. Yeah. Yes.
Yeah.
When it what? Banking, not quite. Oh well.
Thank
You have the right idea. The direction is important. So if the plane was to change direction so that it's no longer perpendicular to the field, then it would lose it. Yeah. So if the plane was to turn east, then it would no longer have this voltage because it wouldn't be perpendicular anymore. But there's another time as well, though.
Like, yeah,
When the plane is what?
like this.
No. Come on. No.
To make that it's 0 to.
When the plane is at cruising altitude, when it's reached its top altitude, because you only get the voltage as it's climbing or if it's descending, because the area is changing. But as soon as it reaches its cruising height, no more voltage, because the area is not changing. The area here is increasing as it climbs, perpendicular to the field. As soon as it reaches its cruising height, no more voltage. So only while it's taking off and landing will it read the voltage across the wingspans. Yeah?
So the area is taken.
Yeah.
Not like.
Not like that. Yeah. The sort of the height rather than the travelled distance. Yeah. 1 volt is quite a lot. You know, you could easily measure that if you could go outside the plane and connect your voltmeter to the ends of the plane. They probably won't let you do that though. I don't think they like when I've tried. They don't like when passengers do this. Okay. So this one is a hard lesson. I think I would like you to try these for a few minutes. It's not easy. Not easy. It's a bit hard, yeah. Let me actually just add something here so I don't forget. So I just want to put here in the notes.
We can see our problem.
I'm just saying rewrite the formula as BLV. BLV. Have you figured out what the word pause does in my It's
Pause. Like
pauses when I split a sentence like this.
Yeah.
Yeah? Ah, it's all right. Okay, let me just open these questions up again for you, and you can start these for a few minutes. And then we'll have a look at the next lesson. Can I close this? I can close this?
Yeah.
You have this? Yep. Okay. Rightio. Let me. Where's it gone? Where's it gone? Where's my PDF? Come on. Ah, there we go. Can you... Sorry, am I going... Oh, there's the PDF. I was just going to ask you if I'm going crazy, but I can see the PDF now. Okay. You can take a picture on your phone or whatever. I'm actually going to...